So let's discuss a new topic, that is bandwidth efficiency versus EB by N naught of M-array modulation schemes. So what we have seen till now in the last lecture, we have seen what is the bandwidth efficiency of a M-array modulation scheme. What do we mean by bandwidth efficiency? The data rate transmitted through the transmitter of an M-array modulation scheme in per unit time and per unit bandwidth. That is why it is called bits per second per hertz. So this we have seen that bandwidth efficiency of MPSK and MQM is log 2m by 2, and bandwidth efficiency of MFSK is 2 log 2m by m, and physical interpretation of bandwidth efficiency is number of or data rate or number of bits transmitted through each signal, each M-array signal in unit time, in 1 second of time, and unit bandwidth. So this is the table. We have used these formulas and we have made this table. From the table it is clear that as M increases, bandwidth efficiency of PSK as well as QAM, MQAM increases, whereas spectral efficiency or bandwidth, this is also called spectral efficiency or bandwidth efficiency of MFSK decreases. So we have only talked about data rate, right? That how efficiently you can utilize the bandwidth of the channel available. Higher the data rate we can transmit in per unit bandwidth, the efficiency is high. We are using the channel more efficiently. But what about the error performance? So for this, what we discussed that we fix the error performance to some value. Let us say we take it 10 to the power minus 5. And we say how much power would be required in terms of EB by N naught to get this much of probability of error for all M-array schemes which we have discussed. So what we are going to do in this lecture, in x-axis we will plot EB by N naught in dB. In y-axis we will plot the spectral efficiency or bandwidth efficiency in bit per second per hertz, and we will see how much EB by N naught is required to get a probability of error. So let us take an example of one point in this graph. What are the various information we can infer from each point? So let us say we take 4 PSK first. So 4 PSK, we first perform 4 PSK and we say probability of error of 10 to the power minus 5 can be achieved by 4 PSK when our EB by N naught is in 10 dB. There is a formula for to evaluate probability of error in 4 PSK scheme or QPSK scheme, that we are not explicitly mentioning here. So I just assume that you know the formula, and the formula tells the 10 dB of EB by N naught provide probability of error of 10 to the power minus 5. So just make a point at 10 dB in EB by N naught graph, and since you are using QPSK or 4 PSK, what should be the corresponding eta? Just go to the table, and the table corresponding to this is 1. So what you are seeing here, that each point provides two information, that in order to get a certain probability of error, which in our case is 10 to the power minus 5, what amount of transmit power is required and how much data rate you can transmit in per unit time and per unit bandwidth. So if you increase your M to 8, I told you that the performance of MPSK scheme becomes poor as we increase M. performance in terms of bit error rate. So performance become poor. It means in order to get same probability of error, you need more power if you increase number of modulation symbols, number of symbols. So just assume that it is around 13 to 14 dB that you can get from the formula. And here, so at 13 dB, you get, for example, 13 dB, you get 10 to the power minus 5 of probability. We are fixing the probability of error, right? And the corresponding eta would be 1.5. Similarly, for 16, as you increase m, as I told you that the performance of the system, MPSK system, becomes poor. It means you need more power in order to get the same probability of error. Therefore, you will get this type of curve, right? And this curve is for PSK. Now try to plot the curve for QAM. So first you need to understand that 4 QAM is same as 4 PSK. That I have already told you in the class, that the constellation of 4 QAM is same as 4 PSK. Therefore, this 4 QAM point will lie at the same. The 2 points will coincide. So if you represent with a square, the cross and square would overlap. It means that for 4 QAM, same amount of power would be required to get the probability of 10 to the power minus 5. And since we know that QAM and efficiency would always be same, will be same. Now if you go to 8 QAM, I told you that performance of QAM is better than performance of MPSK. It means you need less amount of power in order to get the same probability of error. Therefore, this point will be somewhat left to this point. This point is coinciding. Reason because 4 QAM and 4, specifically 4 QAM and 4 PSK is same, right? But it is not the case for m is equal to 8, and 8 QAM is different from 8 PSK. But I have told you that the performance of QAM is better than PSK. Therefore, you will need less amount of power in order to get same probability of error. And since eta is same, you will get this point will be 1.5. So each point is providing you 3 information, that when you use 8 QAM, how much power would be required in order to get this much probability of error. So 10 dB of power is required in order to get 10 to the power minus 5 error, and the corresponding spectral efficiency is 1.5, or this, and this is the probability of error, and this is EV by N naught. So each point is giving you this much of information. So similarly, when you compare 16 QAM, of course for 16 QAM and 16 PSK, the spectral efficiency is same. However, we need less amount of power in order to get the same probability of error. Therefore, the curve would look like something this, right? You can put this value by just from this table to 2.5 and so on. So as you can see, as you increase number of m, what happens? Spectral efficiency is getting improved. However, the power is also getting improved. So eta is getting increased, eta is increasing, but the power required to get same amount of error is also increasing. So what is happening? If you increase m, you are utilizing your system or bandwidth more efficiently. However, your power consumption is more. So this QAM and PSK scheme is preferable for the applications where we have bandwidth limitation. Bandwidth limitation means you want to utilize your bandwidth more efficiently, or you want to send data rate in less amount of bandwidth available. So you need more spectral efficiency. However, there is no such constraint as power, because here you see that in order to get similar performance, or if you increase M, your spectral efficiency improves, means you are using your bandwidth more efficiently. However, you need more power. So if there is no such requirement, or the power is in for the communication or the application scenario where power is not the problem, but the spectral efficiency or bandwidth is, we use COM or QPSK, or sorry, COM or PSK as modulation schemes. We prefer these schemes. And such one or two such applications is telephone line, and microwave, digital microwave communication. Right? Whatever we use 2G, 3G, this is also come under this context. Mobile communication, we use microwaves. Next, we will discuss MFSK scheme. I told you that MFSK scheme, if we increase value of M, spectral efficiency decreases, right? But the performance of FSK is better than QPSK, better than PSK and COM. And what is the reason behind this? Let's discuss it here. I told you that as M increases, in case of PSK, the constellation points become closer and closer. Therefore, error performance, or the performance in terms of error, degrades, right? As M increases, the performance degrades because of this reason for PSK, right? Because the constellation point becomes closer and closer. However, in FSK, what happens, as we increase the number of modulation symbols, we go to higher dimensions because we add more number of frequencies. Therefore, we go for higher dimensions. So compactness does not happen. The two symbols does not come close because we are expanding the space also. Therefore, what happens when M increases, in case of FSK, the performance also improves. So by considering these two logics, we have seen that as M increases, the spectral efficiency of, as M increases, spectral efficiency decreases. So you can just write the values. 64 value is 0.19, 0.31, 64 and 32, 16 and 8. So this is the FSK. But as I told you, the performance, as M increases, the performance of FSK improves. Means you need less amount of power. As you increase the value of M, you need less amount of power in order to get the same error performance. Therefore, this scheme is preferable when we have a power constraint communication application. Power constraint. For example, satellite communication. Why do we call it power constraint? Because there we use solar system or solar charging stations. We cannot charge our communication setup again and again. Therefore, there we have a constraint of power. However, we don't have a constraint of bandwidth because there is no many users there, right? So we don't need bandwidth constraint. However, we need power constraint in those satellite communication scenarios. Therefore, for those scenarios, FSK schemes would be preferable because if you go and increase the number of symbols, your amount, the amount of power which is required in order to get a certain amount of probability of error decreases. Though we face the problem of less bandwidth efficiency, but that is not our, we require more bandwidth, but that is not the case because that is not a problem because bandwidth is not the constraint here. Right. So one more point which we want to add, though we are from the transmitter, we are transmitting or we are increasing the modulation sizes. So we are improving the, for example, PSK, we are increasing the bandwidth efficiency. But it might, we are not taking into account the channel. that for a given EB by N naught, what is the maximum spectral efficiency that a channel can accommodate? You can think it like that, because like you have a pipe and you are inserting more and more and water into it, but we are not thinking about the capability of this or capacity of this pipe. So can we put whatever amount of water or to it, so can we increase the efficiency as much as we like, or there is some upper cutoff on this, or the which is decided by the pipe or the capacity of the channel. So for the AWGN scenario, scenario, this capacity is determined by formula that is called Shannon formula of capacity or spectral efficiency, that tells you what is the maximum spectral efficiency you can achieve for a given power or EB by N naught value in bits per second per inch. So you, for a given EB by N naught, you cannot increase your spectral efficiency beyond this value. Thank you.